Physics is one of the coolest things that you can study, and in this video I want to tell you about 10 highlights that really blew my mind when I was going through the physics degree. There's a lot more, but these are the ones that stood out to me and that I remember very well. So let's begin with number 1. The first highlight is when I took classical mechanics. This was split into two parts. We had classical 1 and classical 2, and the classical 1 mainly talked about Newtonian physics, and classical 2 was mostly focused on the Lagrangian formalism and the Hamiltonian formalism. So in classical 1, I remember this very distinctly. We learned about the tides, and the professor was explaining how there's always two tides that come from the gravitational pull of the moon mainly and the sun, and it's a bit tricky which one exerts a larger tide, but never mind the full details. The gravity from the moon and the sun cause tides on Earth, and you see two tides. Now this is a bit weird. Why should you see two high tides per day? Well, you should think about the fact that the moon is closer to some part of the Earth on one side, and so it tugs on that water a little bit stronger than it would at the center of the Earth. And likewise, it would tug a little bit harder at the center of the Earth than the far side of the Earth, which has the lowest amount of tug from the moon. And the bizarre thing that I remember is that when you change coordinates from just having an inertial observer watching these two systems gravitate, and you move into the non-inertial frame, which is the frame of the Earth itself, you find that the actual tidal field that the Earth fields from the moon pulls sort of inwards in the direction perpendicular to the line joining the Earth and the moon, and then in the direction joining the Earth and the moon, you find that the tides pull outwards. So you get the squeezing effect. There's tidal forces that are pointing inwards at sort of the poles, and then you have these tidal forces pointing outwards along the line joining the Earth and the moon. And this was an eye-opener because this is how the tides work. It's the fact that there is this squeezing mechanism that's happening from the two sides that are perpendicular to that line joining the Earth and the moon. And then the other two sides have a pulling mechanism, and it's only when you combine these two things that you actually get tides. I remember asking my professor, why doesn't a cup of coffee feel the tides if you're at the beach? If, according to the calculation that we were doing, any molecule of water should feel the same force from the moon. And I remember my professor gave an answer that wasn't really satisfying to me. So I went home that day and I watched the video by PBS Spacetime, and there I found the answer, which was that the tides only work when you have a large body of water for this squeezing effect and pulling effect to work out. Otherwise, every single body on the Earth's surface is going to feel the same tug, and so you wouldn't really get tides. What you need is basically two things. You need a fluid, like an ocean, or a large body of water, like a huge lake. And then what you need is this squeezing on one side, pulling on the other side, and that's what causes really the tides on a large body of water. You will not see this effect on small bodies of water because there's just not enough tidal forces or tidal differentials to cause the tides to happen. So when I learned tides in undergrad, that was really one of the highlights of going through a physics degree. Okay, so number 2 is still on classical mechanics, except now it's not classical 1, it's classical 2. And in classical 2, we learned first Lagrangian formalism and then the Hamiltonian formalism. And I want to talk about the Hamiltonian formalism because at some point, what you learn about is that in Hamiltonian mechanics, really what matters is looking at something known as phase space. And phase space is not the same thing as three-dimensional space that you and I live in. Instead, it's a kind of mathematical construct that takes the properties of a particle and puts them on axes and creates a space out of them. In particular, in classical mechanics, you use the position of the particle and its momentum. And when you construct this phase space, for example, you can take a simple pendulum that goes back and forth. You can label its phase space by the angle that it makes and perhaps its momentum as it moves forward. And so you get a very simple two-dimensional phase space of a simple pendulum. Now here is the highlight from Hamiltonian mechanics, and that is if you take phase space and you take a distribution of possible locations in phase space, these might amount to certain initial conditions of your system, then if energy is conserved, if there are no dissipative forces, Louiville's theorem says that the volume of phase space is conserved through time evolution, which means if I start, let's say, with a circle of a certain area in phase space and I let time evolve, this circle might deform into an ellipse and, pendulums are swinging, etc. What is true is that if there's no dissipative forces, that the area in phase space is conserved, meaning that there's reversibility. You can go forward in time and you can go backwards in time without loss of information. And that's what energy conservation gets you. On the other hand, if there are dissipative forces like friction, then you can only go forward in time and you can't go backwards in time because you don't know which initial condition got you to that point. So these dissipative forces spoil this reversibility, and that's where the highlight was, and that Louiville's theorem only works if you have if you don't have non-dissipative forces. So this was highlight number 2 in undergrad. Highlight number 3 is again in classical mechanics, this time again classical 2. And now it's not the Hamiltonian formalism, it's the Lagrangian formalism. And here the highlight is the Euler-Lagrange equation, and more generally just the calculus of variations. Now the reason this is a highlight for me is because when I first learned about the calculus of variations, the example that we did was proving that a straight line is really the shortest path between 2 points in Euclidean space. Now obviously everyone knows this, a child knows that a straight line is the shortest path. But how do you know? How can you prove it using the calculus of variations? And that's what we did, and it was really mind-blowing to see that you can just use kind of the Euler-Lagrange equation or the calculus of variations to figure out that it's a straight line. The answer is a straight line. Now, if you generalize this idea of the principle of least action or just the Euler-Lagrange equation, then you can actually start solving more interesting problems like the brachistochrone problem. And you may have seen this before. Vsauce has a video on it. I think Veritasium has a video on it. But basically the idea is if I have a ball that's rolling on a ramp from point A to point B under a gravitational field, what shape of the ramp would lead to the fastest descent from point A to point B? That's in a nutshell what the brachistochrone problem is. It was developed by one of the Bernoulli brothers, and he sent it out as a challenge. Now, if you use the Euler-Lagrange equation, you can solve the brachistochrone problem, and what you end up with is a cycloid. The answer is a cycloid, which is the path that an element on a bike at the rim of a bike would make as the bike is rolling. So it's pretty cool to learn about the Euler-Lagrange equation. And what's even more fascinating is that this particular Lagrangian formalism shows up in quantum field theory later on when I went to grad school, and it kept coming up again and again and again. And so this really was a highlight that it just stuck with me from physics undergrad. All right, number 4, now we're moving on to electricity and magnetism, and the highlight here is going to be deriving the wave equation from Maxwell's equations. Now, I think if you're a physics major, you've probably done this before, and you know what I'm about to say about the beauty of it all. If you take Maxwell's equations, you get rid of all the sources, so you send the charge densities to 0, the currents, you send those to 0. You just have the sourceless Maxwell's equations, and you try to manipulate them a little bit by taking the curl of the electric field, or vice versa, the curl of the magnetic field, and then you can do very simple Calc 3 kind of manipulations, right? Vector calculus manipulations. And what you find is that after these manipulations, you end up with an equation that has 2 derivatives in space and 2 derivatives in time. And what is this equation? It is none other than the wave equation. And what you just showed is that the equations, Maxwell's equations, give you the wave equation in the electric and the magnetic fields. Well, what is that? What is a wave in the electric and magnetic fields? That's right. It's light. It's an electromagnetic wave. Now here's the best part. Here's the highlight of it all, is that if you do it using the permeability and permittivity of free space, what you find, if you just compare it to the wave equation, is that there's a formula for the speed of these electromagnetic waves in terms of the permittivity and the permeability of free space. And that just blew my mind. You can write down the speed of light c as 1 over the square root of epsilon naught times mu naught in a vacuum. That was a highlight. Come on. If you're a physics major, you know what I'm talking about. That's a highlight for sure. Number 5, again, we're sticking to E&M. This time it's going to be the Poynting vector. Now, the reason this is a highlight is because of the non-intuitive nature of the energy flow in electromagnetic fields. So the idea behind the Poynting vector is that if you have an electric field in space and you have a magnetic field in space, and they can be pointing in all sorts of directions, at each point, you take the cross product between the electric field and the magnetic field, and that gives you another vector called the Poynting vector. And what it describes is actually the direction of energy flux, or if you want to think of it as energy flow per area per unit time. So that is basically what the Poynting vector is getting at. Now, so far, this is just a definition. There's not really much there. But the highlight is when you consider how the Poynting vector works in something like a current carrying wire or just an electrical circuit in general. And you find that the Poynting vector behaves in all sorts of weird ways. It looks like it's going in, it's flowing into wires, and it's flowing out of batteries and stuff like that. It's just mind-blowing to look at the direction of energy flow from this field picture, which is not the same picture you're used to, which is the particle picture. If you look at E&M using particles, then you won't get this kind of counterintuitive way of thinking about energy flow in circuits. So definitely a highlight was learning about the Poynting vector, especially its applications. Number 6, sticking to E&M, we have Fermat's principle of least time. Now, I learned this in a separate optics class, and the mind-blowing part is, the reason this is a highlight is because if you just assume that light takes the path of least time from point A to point B, let's say I know that light started here and I know that light ended over here, and there's some stuff in between, and I want to figure out what is the path that light took to get from A to B. If I assume that light takes the path of least time, then I can derive the law of reflection. I can derive Snell's law, or Ibn al-Haytham's law, and I can just explain straight up how mirages work, why light appears to bend over hot air and then it just goes into your eyes, so you end up seeing the sky on the road. And this could all be explained if you assume that light takes the principle, or light takes the path of least time. So Fermat's principle of least time really simplifies optics into a very simple set of rules that you can derive just by assuming that light takes the path of least time. Now, this turns out to be heavily related to the Euler-Lagrange equation that I brought up before, and they are all related together to what's known as action principles, or principles of least action. All right, number 7, this is somewhat of a weird thing. It doesn't really come up that much in undergrad, but I'm glad my professor talked about it in a quantum mechanics course. The highlight is known as the Laplace-Runge-Lenz Vector, and this thing just absolutely shredded me. It teared me apart. This was an insanely menacing highlight of my undergrad. And the idea is this: if you take a hydrogen atom and you just compute the energy levels, you find that there is a lot of degeneracy in the energy levels. A lot of the energy levels have the same energy. That's what degeneracy means in the context of the energy levels of hydrogen. And one question is, why is hydrogen degenerate like this? Why does it have energy levels that a bunch of them are all equal? And the reason ends up being that there's a symmetry in hydrogen that is a symmetry in 4 dimensions. Because the way the Coulomb attraction works between the electron and the proton, then there's an additional symmetry that is not directly apparent. If you consider the symmetry from the force, which is the symmetry in 4-dimensional rotations, never mind the full details, you find that this symmetry gives you these degenerate energy values for hydrogen. Now, that's not all. There's an even better way of looking at this Laplace-Runge-Lenz vector, and that is that if you look at orbits, the Kepler problem, if you have 2 bodies that are gravitating using Newton's law of gravitation, you will find the same symmetry applies to Newton's law of gravitation. And how does it manifest when you talk about gravitating bodies in the Kepler problem? Well, the way it manifests is that the ellipse that planets take around the big body, the sun, for example, this ellipse is fixed in space. It does not precess, which is not what we see in nature. We see Mercury's orbit precesses, but to a good approximation, the precession of, for example, Earth is basically minimal. And that's exactly because of this 4-dimensional symmetry given by the Laplace Laplace-Runge-Lenz Vector. So highly encourage you to go read about this and look it up. Definitely one of my highlights in undergrad. All right, next we have something in quantum mechanics, and this is the idea of identical particles. This was really trippy when I first learned about it, but it's also really fascinating. Consider this. If I have a single electron just sitting there in space, then the way to describe it in quantum mechanics is to just give it a wave function in space, and that's it. That's all you need, just the wave function of the electron, and then you can do a bunch of math, Schrödinger equation, blah, blah, blah. But what happens if I have two electrons? And I know I'm working with two electrons. Well, the math says you can't write down the wave function for this electron and the wave function for that electron because you don't know what is this or that electron. And what ends up happening is that you have to really write one wave function for this combined system. And you just don't know what is electron number 1 and what is electron number 2. You're not even allowed to label these electrons that way. And so the concept of identical particles forces you to write one overall wave function for a system of particles. Now here's something even more fascinating. If I have fermions, which are what electrons are, they have spin 1/2, then the wave function has to be antisymmetric, meaning if I switch the locations of or the properties of these two electrons, then the overall wave function has to flip sign. It has to gain a minus sign. Whereas if I have bosons, so light, for example, is a boson, then the wave function is symmetric, meaning if I flip two bosons, the wave function does not matter. And what happens is you can, the consequences of this is that you can store as many bosons as you want in the same quantum state, no problem. But if I take two fermions and I put them in the same quantum state, well, this anti-symmetry of the wave function means I get 0. And if I get 0, then that's not possible to have these two things in the same quantum state. So this is the Pauli exclusion principle in action. So this was an amazing highlight that I learned in quantum mechanics in undergrad. All right, the next highlight has to do with thermodynamics, and this one is still, it trips me up, but not gonna lie, when I first learned about it, this also blew my mind, and that is the idea of negative temperature, which turned out to be really hot, like really, really hot, like, you know, off the charts hot. And what's the idea there with negative temperature? The idea is that if you take a statistical mechanics point of view and you try to understand what really is temperature, well, temperature kind of tells you about the way that the subsystems, I guess, or the microstates fill up the energy levels. So if I have a higher temperature, that usually corresponds to particles occupying higher and higher energy levels. So the more you ramp up the temperature, then the higher the energy levels are filled. But what usually happens is you have to start from the bottom. You have to fill out the lowest energy levels before you can climb up to the higher energy levels. But what you can do is you can prepare systems, and this has been done over and over again, by which what you can do is you can have things fill up the highest energy levels first, and it has the opposite effect. You don't fill the lowest energy first, you fill the highest energy first. And it's still weird how that works. I haven't fully grasped my mind around it, but from what I understand is you have to, at some point, you know, physically manipulate the system, flip it around the energy levels to kind of force it into this metastable state. Regardless of the full details, which I'm not completely 100% on, you can have states with negative temperature that behave in sort of an opposite way that what you would expect. All right, lastly, the one that rules them all, the highlight of undergrad, and that is learning that quantum mechanics can explain the periodic table. This was just mind-blowing. It was amazing. It was out of this world. The fact that you start with something very simple, and that is the Schrödinger equation, and you start with Coulomb's law, and you just do a bunch of math on this simple quantum mechanical system, for example, hydrogen, and you start working out the quantum numbers and the energy levels and what you should expect, and you find that you can fill up energy levels the exact same way that the periodic table is filled up. You start with hydrogen, and then you have helium, and then you saturate the energy levels, and then you can talk about the next energy levels and how many electrons you can fill, and why is it that you can fill this many electrons, and why is it that the electrons have their spin states, and their spin states can't be in the same spin state, and all of this, the entire periodic table, the structure of the periodic table, can be explained by simply the rules of quantum mechanics. If you take the rules of quantum mechanics, you can explain the entire periodic table. That, I mean, if that's not a highlight, I don't know what is, right? You learn in school this magnificent thing called the periodic table. You learn that these things seem to share properties, and you always wonder, like, why is it this way? Why is it that I have to stick 2 electrons here and 6 electrons there and blah, blah, blah? The answer is quantum mechanics. From simple rules of quantum mechanics, you can derive basically the entire periodic table. So that's it. That's my list of the top 10 highlights from undergrad. There's a ton more, but these are the ones that I just, decided to remember for you for this video. Maybe I'll do one for grad school as well. Over there's also a ton of things that I learned that just blew my mind, most of them from quantum field theory and particle physics, but also cosmology and statistical mechanics. So stay tuned for that. If you watched up to this point, hit that like button, hit that subscribe button, and if you're interested in supporting me, I do have a Patreon, links in the description. Peace.